Hello and welcome back. Today we're going to keep deep diving into the Cisco Cache Engine 505 that Collab Retro sent over for repair. Last time we went and looked through the hardware architecture, seeing that it was largely a PC, and then went through and developed a recovery procedure to be able to restore the vital product data in the system that was preventing it from booting. But we didn't really get into the software details of how I figured out what that vital product data is and where it existed in the system. So today we're going to take a couple more steps about how I figured that out and get into some of the reverse engineering that needed to happen. First, let's go back and look at the failure mode that was occurring when the device first arrived. So we have the system booting and it goes through its normal BIOS boot process and ultimately ends up in this Cisco Cache Engine boot, which appears to be a built-in bootloader in the system. This goes through an auto boot process where it says that it's attempting to boot from a flash device, and we know that there was a NAND flash device on the system. We get a dump out of some information, including this message about starting at 0x108000, as well as a dump of some basic information about the Cisco CE image, which I assume to be the OS image, before we get an error message that says, this image supports models CE505, CE550, and this appliance is obviously there's a word missing there, but we don't know what, and we don't know why. So what I really want to do is go figure out where that error message gets generated from and let me work back from that point to figure out what is it supposed to be printing there, what information is it using to figure out what to print there, and hopefully that'll give us some clues about what the vital product data actually is. But first things first, we need to actually start with what we have available in the system. So if I look over here, these are all of my dumps of the non-volatile storage from the CE505. And we know that we can exclude a couple of these right off. First of all, the two network card EEPROMs, as we discussed last time, simply aren't used. They contain nothing of interest, and they wouldn't include any code anyway. When I went through the hardware architecture, I noted that there were two separate flash devices, one for the BIOS and a separate NAND device that we didn't actually look at. My hunch is that the messages coming from the bootloader indicate that we've gotten through a first stage bootloader that's likely contained in the BIOS image, and that it's actually trying to load some software off of the NAND device. Now, I didn't want to remove the NAND device from the system because it would require desoldering it and resoldering it, which is kind of risky for a device of this age, and it seemed unnecessary at the time. Now, I've already sent the device back to Collab, and we'll just have to live without the contents of that. But it means that I'm going to steer my investigation a little bit over to the hard drive images first, because I think we're actually getting out of the BIOS. So let's take a look at the first hard drive image and see if there's anything of interest. The very first thing I'm going to start with is just running the file command on it. Now, for those unfamiliar with Linux or Unix tools, file is just a tool that looks at the file and tries to identify if it's a known type of file. So in this case, it looks at, and it quickly identifies that it actually has a DOS partition table on it with a couple of partitions. Now, if we want to see that a little bit more easily and in a little bit more of an informative view, we can simply go ahead and run fdisk on the file itself and get a dump of all the information. So it looks like this drive had 3 partitions on it. Now, the overall drive image was a 9 GB drive, and it looks like the first 2 GB of that is actually a FAT16 DOS partition type. Then there's a 512K section that fdisk is calling a partition magic recovery partition, but I'm pretty confident that this is not what that is, that simply the ID has been reused by something else that Cisco was doing. And then the bulk of the disk is actually used by this unknown partition type. Now, the documentation for the CE505 talks about the cache file system, which was where all of the files for the transparent proxying were stored. So I'm going to assume that that large file system or that large partition actually contains the CFS file system. We just don't have any details on how that file system works, so I'm not going to be able to really dig into that part of it, and it really should just be cached web objects in the first place, which would only be interesting to see what the last user of the system actually had in the cache. But the easiest thing here is that the first partition is a DOS partition. We should be able to just go ahead and look at that directly. Now, some of you may be familiar with doing a mount-o loop, where you can say, I want to mount this particular image file to some folder. Now, that works for things like floppy disk images where you don't have a partition table, because mount is actually trying to mount a file system. But mount does not deal with partitions. So in this case, where we have a drive image that contains 3 different partitions with a DOS partition table, we actually need to do a couple more steps. Instead of using the mount-o loop, we're going to use the lo setup tool. lo setup lets us interact with the kernel and set up a separate loop device that will then point to the contents of the file. So we're going to go ahead and run lo setup-f, which just says to go allocate the next dev loop device node, and then simply give it the file that we want to actually create, or that we want to attach. Now if I run lo setup, it comes back and says that dev loop 0 is connected to the backing file of our image. And these are other things that you can adjust for if you want to limit the size or if you want to look at a particular range of the file as a device. But in our case, we don't. So now if I run fdisk on dev loop 0, I get the same information. I get the partition table. But you'll notice that it says here dev loop 0 p1, p2, p3. But if I look in dev loop, I don't have those devices. I only have dev loop 0, which is the entire disk. So we need to tell the kernel that I just attached this new device and that I need it to actually go look at the partition table and create the partition nodes. So by running the part probe, I now have my 3 different partition entries. So finally, we can create a directory to attach the file system to, and now we can finally mount our drive image onto that directory. So what do we have inside? Well, just based upon the file names, I'm going to guess that these first 2 files, the CE505- files, are related to the OS in some way. Now, being a .bin just says it's a binary file. Usually that means it's executable, but not necessarily. And .pax is typically an archive format. There's a specific format called pax, similar to like a tar or a zip file. But one interesting thing here is if I run file on that pax file, it comes back and says data, which means that it doesn't meet the format that we would expect for a normal pax archive. It would actually come back and tell me if it was. So while pax is an archive format, it looks like perhaps whatever operating system is being used on the CE505 doesn't actually use the standardized pax, but probably some other variant of it of their own making. In the rest of the file system, there's just a lot of interesting little tidbits. If we look in etc boot, it looks like the actual boot process is done with TCL scripts, which TCL is a scripting language that was popular in the 90s and is still popular with FPGA and chip development tools. Kind of an interesting and unusual choice at the time. But these are scripts that would actually run after we've booted the OS image, which we're not even getting that far. So similarly, when we look in /lib, we have more tickle scripts. We also have a bunch of the GUI assets, which seem to be mostly image files. GUI image, there you go. And in var, we just have log, which does include a syslog, but mostly it's just the normal boot up sequence from the last time the system was started and then when I started it myself. There's not anything of particular relevance to what we're looking at, so we're just going to skip it. So that leaves us with this _UVACL_.db, which is a Berkeley database file, which could be interesting to look at, but it also says ACL, which tells me this is most likely an access control file. So I'm just going to ignore that for now, because again, this is probably once the system is up and running. So we have one file left, which is this bin file. And based upon the name, I'm going to guess this is actually an OS related file for version 251. Now if we run file on this, it comes back and tells us that this is actually an executable binary. Specifically, it's in the ELF file format, or the execute and link format, which is the standard format for executables on modern Linux and Unix systems. In fact, if I run that on file on binls, I come back and it tells me that it is also an ELF file. There's a lot more details here. We can skip over a lot of what that means. But the main thing here is that this just says it's a 32-bit x86 binary and that it's all kind of folded together into one binary. It doesn't need to load any additional libraries in order for it to function. But what about this ELF format? What is that going to tell us? What information can we get out of that? Well, if we look at the ELF file format, you end up with a binary that's really split into three pieces. One is a top-level header that describes that, yes, this is an ELF file, and points us and provides some basic information about it. And then there's two pointers inside of that header that point to the other key sections, which are the section headers and the program headers. Program headers tell an ELF loader which parts of a file to copy into memory and where to place them. Each header describes a region in the file in terms of an offset from the beginning of the file and a length for how many bytes to copy, called the file size. There's a corresponding virtual address that describes where in memory to place it, and a mem size describing how many bytes of memory will be used. Note that the mem size can actually be larger than the file size. When that happens, any additional bytes not used by the file size are zeroed for use by the application. Note that program headers don't say anything about the contents of the data being copied. That's the job of section headers. Section headers attach a human-readable name as well as some additional attributes to various ranges of the file. Section headers can also include memory addresses describing where that data should be copied to, which ultimately gets turned into program headers late in the linking process. Unlike program headers, which describe only the portions that need to be copied into memory, section headers describe every byte within the file, even if that data only exists on disk and is never copied into memory. So let's go look at our binary here, and we're going to do that with the objdump tool. And -x says, please dump out all of the headers contents. So we end up with, at the beginning, we know that this is an i386 binary. It's an executable as opposed to like a library file or an archive or a couple of other different types that are used more during the compilation process. We know that the start address of the program, so basically the entry point or where the loader should jump to start execution of the program once the program's been loaded, which interestingly is that same 108000 that in fact gets printed out during the boot process. Then we have the program headers, which tell us that we're going to copy three different segments. Now, looking at the section table gives us a little bit more detail about what's going on. In traditional Unix programs, the text section is where you put all of the executable code. So note that that's actually going directly at that 108000, and that makes sense. We're going to jump into that, and so the actual code is at that same address. The entry point is going to jump into the beginning of that code segment. Data is what it says. This is initialized data. This is where the contents of variables or other things like a static variable that has an initialized value will get stored, and so those also get copied in. And that's actually going to be fairly close to the end, if not directly after the text segment. The BSS segment is for uninitialized variables, or basically space that you need to have allocated for the program to run, but there's nothing actually to copy into them. They don't have an initialized value. So this is where we end up with a bunch of that extra memory space, where it's going to actually just allocate that space, but it does not load or have data. Now, the next couple one here are very, very, very interesting. One, we have this image.info, which notice that there's no load at all, or alloc, which means that this just exists in the binary file, but never actually gets copied in. It's not part of any load command at all. So we'll have to look and see what's in there. Then we have what's actually at that 200,000 hex, which they call image.zip, which is a very interesting name. It probably means there's a zip file embedded inside of the executable. And then at the 400,000 hex, we have this image.checksum file. So how can we get those pieces out of this? Well, we have to turn to another tool, objcopy. Objcopy lets us copy contents from one binary file format or one executable file format into another format. So before we start messing with this with objcopy, which has a potential for modifying the binary, we're actually going to go ahead and copy the bin file to our local directory. So then we can use the dump section command right here to dump the contents of a particular section into a separate file. So we'll say objcopy dump section image.zip equal image.zip of our binary. And so now I have image.zip, which if I run file on it, tells me it's a zip archive, and I can even look at the contents of it, which we'll get into in a little bit more here, but to show a little preview, the OS image that we're actually going to deal with is VxWorks. So what else is in that binary? We had a couple more sections that we wanted to look at. So let's go ahead and get the info file and the checksum file. Now, interestingly, those two files appear to be exactly the same. So if we dump one of these, we get this bit of information which looks like a text file, so let's just go ahead and dump it that way. And sure enough, this is that blurb that gets printed out during the boot process telling us that the OS image, what supported products it has, and what the checksum and compressed and uncompressed sizes are. So essentially they pack in a loader as well as the OS image itself into a single ELF executable. And so the bootloader is going to load this loader, which is the ELF executable, which is going to then somehow get the contents of the zip archive into memory and actually execute them. So let's go ahead and unzip the zip file. And we know that we have this VxWorks file. Now this is an actual VxWorks OS image. If you're not familiar, VxWorks is a commercial operating system typically used in a lot of appliances like routers and other things. And it's a very old operating system, still commonly in use, but given the vintage, this is going to be an older version. And maybe we'll get lucky here. Let's see, is VxWorks something simple? Oh, no, it's not an ELF. It's an a.out. Okay, what is an a.out? The a.out file format is the predecessor to the ELF file format, at least in the Unix world. It's a little bit more primitive, but does much the same function of describing how to actually get the binary loaded into memory so that you can jump into it and start executing it. Now, where ELF actually contains a header that points to other sections, an a.out simply has a sequence of data that's going to be in the file. So the exec header doesn't tell us where things are located in the file. It simply tells us how large they are. And then we're expected to follow this in the order of that information. So in that main header, we get a few things. We end up with, the size of the text segment, the size of the data segment, the size or how big the BSS should be. Then the symbol table size. Then we get the entry point address, and then we have these relocation tables. And so just like what happened in ELF, you would figure out, oh, this is the text segment, this is the data segment, and load those into RAM, and then you would ultimately you would clear out the BSS segment, and then you would jump into the executable. Now, the big challenge here is that this format does not tell us where the binary actually gets loaded into memory, or what its expected address is. We know where we're going to start executing the program, but not where it's actually going to exist in RAM. So we need to figure that bit of information out. And that's where we're going to start getting introduced with a tool called Ghidra.